All right, sorry about that. My internet connection went out briefly. So let me reconnect my other device. Share my screen. Okay, where was I? I was saying that we program a computer to say, all right, I want to try a bunch of different Y2 values. For each Y2 value, I'll have to send light in at an angle given by that, which means I'll have to apply some voltage to the piezo to tilt the mirror, push the mirror in such a way that it tilts at this angle or that angle and hits the point we want. Any questions so far? All right. So that's the task of the scan lens. Now, the thing is that with the scan lens, you have to cover a pretty wide range of angles. And so we generally do that with a pair of lenses. That way we can put the mirror very close to the lens rather than having to put it a focal length away. So what people will often do is set it up like this. Pretend that these lenses are the same. You put the mirror as close as possible. And then what you do is you focus the rays so that they hit halfway between the two lenses. And this angle is theta 1. This is F tan theta 1. And then the rays come out at the same angles that they came in at. Right, that's the basic idea, to send all of them like that. Other issues, we need to think about field of view. Okay, field of view is a big issue in this paper. Ultimately, how far off axis we go is controlled by theta 1. Okay, so Y2 must be F objective, F scan, tan theta 1 over F2. And this would be Y1. So I had you work through some scenarios involving that on the homework. And it really just comes down to thinking, okay, what field of view do we want in the object plane? This is our Y2. This is going to set our field of view, and then work backwards. That's not the only issue, however. We also have to think about the size of the lens itself. So if we have this light coming in, the light comes in with some beam width. Oops, that should have been a line. Well, there, that's basically a line. I'll call this 2R0, 2 times, or 2RI, 2 times the initial beam radius, which is the beam diameter. And all of those rays, this is just a cross section of the beam. This is not a mirror, this is just a cross section of the beam, right? It is going to hit at a distance, usually this is about a focal length away. It's coming in at an angle theta. So it will have traveled up a distance F tan theta. All right. And so it will cover now a distance R naught plus F tan theta. The F number of the lens will be the focal length over the diameter, which will be 2 times all of that, 2 R naught plus F tan theta, because that's how much it could move across the lens. Actually, it should really be 2 F tan theta, because we could shift all of this up and down by tan theta. So let me fix that. I divide top and bottom by F. I get 2 R naught over F plus 2 tan theta. Now, generally, we want the F number to be much larger than 1. We want the focal length to be larger than the diameter, because you have aberrations if the focal length, you have to worry a lot about aberrations if the focal length is comparable to the diameter. All right. So typical beam diameter might be R naught would be roughly 1 millimeter. The F naught might, the F of the objective, the focal length of the objective might be equal to 2 millimeters. Let's think about the field of view, because the field of view is what's going to determine tan theta. Tan theta is equal to your field of view over the focal length of the objective, which might be, say, 0.3 millimeters. We might want a few hundred microns above axis and a few hundred microns below. And those are typical numbers that they talked about in the paper. So you're going to need 0.3 millimeters over a few millimeters. All right. And so tan theta might be 0.15 or less. I think in this paper, it was actually, the denominator was 7.2, and this would be 0.36. In which case it's going to be 0.05, my bad. Right, so your F number is going to be 1 over 0.05 plus 2 times 0.105 plus 2 times the beam radius 1 millimeter over FT. Any questions on that calculation? Remember, this is the tube lens, because ultimately this light is hitting the tube lens. And the light could shift up or down on the tube lens by usually something comparable to its focal length, at most its focal length, often less, multiplied by tan theta. And we know that tan theta is going to be pretty small, because if we have an objective with a 7.2 millimeter focal length, which is a number that came up in the paper, and we have a field of view that's 0.36 millimeters, then the angle that the light has to come into the objective at is going to be given by this. Tan theta is that small number. Well, that's good news. That means that the tube lens will not have a lot of aberrations, or we won't have to worry about aberrations in the tube lens. If the light is coming into the objective at such a small angle, true or false, does that mean we don't have to worry about aberrations in the objective lens, the lens that's focusing the light to a small size? Let's think about what's going on with the objective lens. The objective lens often has a radius of just like a millimeter or less. This might be 0.5 millimeters. And this might be, say, 2 millimeters. Sorry, for these, it's going to be different than that. It's going to be more like, well, they told us in the paper, it's going to be an NA of about 0.3. So they told us what that will be. All right, so this angle, which I'll call alpha here, can we ignore aberrations in that case? Is sine theta small enough that we could just use the first term in the Taylor series? We could say sine theta is roughly theta.
Yeah, I think so.
Let's see, we can ignore aberrations if sine theta is roughly theta. So let's take the arc sine of 0.3. I'll just go into my calculator app, clear my history. Where are my inverse trig functions? Arc sine 0.3. That's 17 degrees. And then I'm going to multiply that by 3.14 divided by 180. It's close, but it's not close enough. All right, in practice, when you work with angles that large in Zmax, even 17 degrees in Zmax, you start to see significant, in Zmax, if you work with angles that large, you start to see significant aberrations. Think about this. When we did that Zmax assignment, where we checked to see if we were in the aberration limited regime or the diffraction limited regime, what was the value of the numerical aperture at that crossover point? Does anybody remember from that assignment where you had to check for the crossover between diffraction limited and aberration limited?
You're asking us for the NA for the optimized lens and
Yeah.
correct. Okay. I believe it's around like 7, right?
The NA was 7, sine theta was 7, Kenneth?
Oh no, not wait. Yeah, wait, let me check.
Was it 0.07?
0.06, 0.07, somewhere around there. Which is much less than 0.3. So this is definitely not a situation where a single lens would be with diffraction limited. You'd have to use a highly optimized objective of many lenses, otherwise you would get aberrations. On the other hand, for the tube lens, the tube lens is on the edge of the diffraction limit. It's right at the edge. It's right where the two effects are comparable. Because at this point, you can't say, oh, there's no diffraction, there's no aberrations there. No, there are definitely aberrations. It's just that they're sort of equally strong as diffraction. So we know that the tube lens is right on the edge, which means the tube lens requires an optimization job. That's one of the lessons of what this guy did and why he did it. So here are the things I want you to take away so far. I want you to take away that if we plug in some plausible numbers for the field of view, a few hundred microns or a fraction of a millimeter, and the focal length of the lens, which in this case was 7.2. Even though I read the paper when it's 7.2, I have 2 millimeters stuck in my mind now and forever, because for a long time I used a microscope with a whose objective had a focal length of 2 millimeters. And so that is always going to be the first number that pops into my mind. I apologize for that. But you can figure out what the field of view would be. You can figure out what that angle would be by saying, what is the field of view? How far off do we want light to be in the object plane? And then what angle would we need? And you can calculate that in terms of the objective. All right, so at this point, we've already gone for a while. I don't want to take a break and then just come back for a short time. So I think I will just try to go through this paper. And the way I read a paper, the way most people read a paper, is I start with the figures. So we've got our scan lens. What you should see is that the scan lens takes different angles, maps them to all of the rays that were at the same angle, come together at the same point. So all the red rays were at one set of angle, were at one angle. They come together at one point. Initially, they were at different positions. All of the green rays were at a different angle, and they too come together at one point. They continue to spread out. They hit the tube lens. Now, interestingly, if we look over here, we see these 3 points. It's tempting to assign a lot of significance to them, but these 3 points were rays that came in at different angles initially, are all coming together. It's kind of a coincidence, because here we've got rays, like let's look at the top red ray after it hit the scan lens. You see how it's now, let's look at the middle red ray. You see how it's going parallel to the axis? And the middle green ray is going parallel to the axis. And the middle blue ray is going parallel to the axis. Well, these 3 rays are going parallel to the axis before they hit the tube lens. So they have to come together at the same point before they hit the, they have to come together at the same point in the focal plane of the tube lens. Except in reality, We never have the red, green, and blue rays coming together at the same time because these are different orientations. They're produced by different orientations of the scan mirror. All right. So these three red rays are now coming together at a different angle than they were coming at over here. Coming in at a large angle over here. They're coming in at a smaller angle over here. They hit the objective, they get focused. And then what the author does is he runs through a series of lenses. He starts with the standard Thorlabs lens that they normally used for this setup. And he looks to see, as we take the rays further and further off axis, what will the wavefront error be? And he says that in order to get diffraction limited performance, you need a wavefront error of less than 0.1. Woo. As soon as you take it off axis by more than a few degrees, you are above that diffraction limit. So he says that's a problem. He also looks at the focal shift. And he plots focal shift on the horizontal axis and angle on the vertical axis. And this angle is the range of angles that he would need to go through in order to go up to 320 microns off axis. In order to focus 320 microns off axis, you would have to go out to 14.3 degrees. And he's getting quite a shift in the focal length position. We'll talk about F theta error later if we have a chance. He does this for both the scan lens and the tube lens, and he finds that both of these lenses are frankly pretty awful, right? They're well outside of the diffraction limited regime. So then what he does is he just optimizes one custom achromat. And in part A, he's using Gauss. Let me check something here. Scan lens, why did I see? Something that doesn't quite make sense there. We'll worry about that later. Again, a customized achromat. And with a customized achromat, he's able to get below the diffraction limit for a pretty wide range of cases. Now, these are used as scan lenses for 3mm and 6mm beams. So he's comparing two different apertures. When he's working with the 3mm beams, he gets, oh, we'll deal with that later. What you should notice is that the axial focus shift is much smaller in both cases. If we look at the focal shift, it's like 2 millimeters in the first case and 0.2 in the second case. Up above, it was like 8 and up to almost 3 millimeters. Then he decides, okay, let's assemble what's called a Plössl type scan lens. A Plössl lens is just a pair of doublets. It's a doublet of doublets. These are achromatic doublets. This is a pair of lenses that were just put together, made from two different types of glass, so that their properties would kind of cancel out and you'd get similar performance for a range of wavelengths. And so he just says, let's take two off-the-shelf lenses, put them together. he gets below the diffraction limit for a larger range of angles than he did initially. But still not that much better than what he did with his own optimized lens. Kind of close. In the second case, I would say it's arguably worse. Yeah, it's definitely worse in the second case. Then he designs his own pair. Instead of taking 2 off-the-shelf doublets, he just takes his own pair of doublets. And lo and behold, until you get to the farthest off-axis angles, he is below the diffraction limit. The wavefront error is small. And now you should see that the axial focus shift, the movement of the focal point, is less than 1 millimeter in one case, and it is just a few hundred microns for the other case. That's very good news. Then he stops requiring symmetry. He just says to Zemax, all right, let's do an optimization. And basically, let's get rid of the pickup requirements. Let's not require that this lens be a mirror image of the other lens. And it's getting even better. And then finally, he says, wait, why do we really have to even require doublets? And when he just does a very deep scan of possible cases, he gets even better performance still. And what I basically want you to take away from this is that one should not automatically trust off-the-shelf things, or at least one should not automatically trust the first off-the-shelf thing that you find. I've given you assignments where I said that an off-the-shelf thing, that a couple of off-the-shelf lenses may be better than one highly optimized lens. I don't want you to go too far with that lesson, because while a couple of off-the-shelf lenses may be better than one highly optimized lens, that doesn't mean that 2 or 3 highly optimized lenses won't be better than 2 or 3 off-the-shelf things. Someone must have a question. Let's talk about this F theta error, okay? Ideally, you would like to have, even though we've been saying all semester, y equals F tan theta, generally when people scan, they're not, I mean, yes, of course they're changing tan theta. Tan theta changes whenever they change theta. But if the object is tilting at a constant rate, then it's theta that is changing at a constant rate, which means tan theta is changing at a non-constant rate, which means that although you're sampling angles at evenly spaced time intervals, you're not sampling y positions at evenly spaced time intervals, which means you're delivering more light to some positions than others and collecting more light from some positions than others. And so F theta error is something that he talks about here. And he is, if we just go back to the very first case, F theta error was 12% here and 3% there. Whereas when you go down to his final optimized case, F theta error is just slightly over 1% in pretty much all cases. So this is an example of a task that you might have to do in a research lab. He doesn't try to redesign the entire microscope from scratch. He doesn't try to redesign the thing that has the most stringent performance requirements, the objective. He just tries to redesign the scan lenses, which are performing, I won't call it a trivial task, but I will say a less complicated task than the other ones. And it is doable with the tools and technologies that you've learned here, which is why I like this paper. Any other questions on anything? All right, next week we're going to start thin films. When we do thin films, I'm going to, we're going to use a Python program. And so you're going to need something that runs Python. You don't need to know how to write Python code. The only thing you're ever going to need to know is how to change the values of a few variables. And make sure you have some kind of Python interpreter working on your machine before next Tuesday. And then next Thursday, we'll have our final alumni visitor, a recent graduate who is now working at a company where he does a lot of thin film work. And he actually did his senior project on thin films with me after taking this class. And so he's going to talk about what he does in the thin film industry. So that'll be next Thursday evening in the second half of class. Have a good day.